Hello and welcome to another Algebra 1 video tutorial. In lesson 12.3 we will be looking at the factored form of a quadratic function. Our goal will be to learn the advantages of the factored form of a quadratic expression in interpreting the graph of a quadratic function. So in the big idea here, the graph of the equation of y equals a times x minus r sub 1 times the quantity x minus r sub 2 is a parabola that intersects the x-axis, so it has x-intercepts, at r sub 1, 0 and r sub 2, 0. Okay, so we're going to look at three forms here. We've just been studying vertex form. So something, let's say we have y plus 4 equals the quantity x minus 3 squared. The key aspect here would be the vertex. In vertex form, we get the vertex. So key point would be 3, negative 4. The form we're looking at today is called factored form, and it's going to look like y equals the quantity x minus 1 times the quantity x minus 5. The key aspects will be the x-intercepts would be at 1 and 5 because that's when y is 0. 1 minus 1 is 0. 0 times negative 4 is still 0. So that's an x-intercept, as is 5, because 5 minus 1 is 4, but 5 minus 5 is 0, so 0 times 4 is 0. And that's what the y-intercept is. X-intercept, excuse me. Okay, and then the standard form, we looked at that in chapter 9. Y equals x squared minus 6x plus 5. The key point on this is probably just the y-intercept, because if we plug x's 0 in here, 0 minus 0 plus 5, y-intercept of 5. Now these all three are the same equation, same graph, same equation. They're just in different forms, so you should recognize what the key aspect of each form is. A vertex form, factored form, which we're looking at today, or standard form. All right, so the equation y equals ax squared plus bx plus c, it's in factored form when it is written as y equals that a value up front times the quantity x minus r sub 1 times the quantity x minus r sub 2. So that leads us into the factor theorem for quadratic functions, and that gives us the x-intercepts of the graph would be at r sub 1 and r sub 2. Okay, so example, let's say y equals the quantity x plus 4 times the quantity x minus 2. What are the x-intercepts of its graph? Well, it's not much different than if we had the zero product property. So let's say we had 0 equals a times b. So zero product property from lesson 2.8, that says either a is 0, b is 0, or they're both 0. That's no different than if we had a here, b here. What value makes this quantity 0? Well, negative 4 does. So one of the x-intercepts would be negative 4. So we'd have the point negative 4 is 0. And that's because negative 4 plus 4 is 0. And it doesn't matter that over here would be negative 6, because 0 times negative 6 would be 0. So we're looking at when on an x-intercept the y value is 0. So what makes y 0 in this case? Now the other one would be 2, because 2 minus 2 is 0. So the other x-intercept would be 2. So 2, 0, and negative 4, 0. And the main thing is kind of because of the zero product property, or the factor theorem for quadratic functions. But you wouldn't even need this theorem if you understood the zero product property from lesson 2.8. All right, consider the equation y equals the quantity x minus 3 times the quantity x plus 2. A, find the x-intercept of its graph, and then b, graph the equation. So we'll need to get some key points here. So the first one would be an x-intercept of 3, because 3 minus 3 is 0, 3 plus 2 is 5, but 0 times 5 is 0. So the first key point would be 3, 0. The other one would be negative 2, because negative 2 plus 2 is 0, negative 2 minus 3 is negative 5, but 0 times negative 5 is 0. So the other key point would be at negative 2. Now, this opens up because there's an a value of 1, but where's the vertex at? Well, we can't get that real easily, but we know the vertex is going to occur. It's symmetric, so it's got to be halfway in between the x-intercepts. So we need the average of the x-intercepts. So negative 3 plus, actually it was 3. 3 plus negative 2 divided by 2. So that would be 3 plus negative 2 is 1. 1 divided by 2 is a half. So the x-coordinate of the vertex is at a half. What's the y value? Well, that's pretty easy. We just put 1/2 in for x. So it's going to be into the original equation. So 1/2 minus 3 times the quantity 1/2 plus 2. So this is going to be 1/2 minus 6/2. This is going to be 1/2 plus 4/2. Okay, so that would be negative 5/2 times 5 halves, which gives us negative 25 fourths. So the y coordinate of the vertex is negative 25 fourths, or negative 6 1/4. So the vertex, which wasn't that easy to get, but we can get this, is at 1/2 and negative 6 1/4. So we go to 1/2 and down to negative 6 1/4. So 1, 2, 3, 4, 5, 6, and down about 1/4. So the vertex is roughly about right there. We get the y-intercept. That's another key point. On a y-intercept, the x value is 0. So 0 minus 3 is negative 3. 0 plus 2 is 2. Negative 3 times 2 is negative 6. So the y-intercept is at negative 6. So it'll be at that point right there. And it's symmetric, so there's going to be a point there at 1, negative 6. All right, we should have enough to graph this. We got all the key points. So the graph is something kind of like that. So we have x-intercepts, the y-intercept, and the vertex, all from this factored form. Now, the x-intercepts were the easiest to get from factored form, but as you can see, we can get the other two key points as well. All right, consider the equation y equals the quantity 2x plus 3 times the quantity 4x minus 1. A, find the x-intercepts of the graph, and then B, find the vertex. Well, the x-intercepts of this are not going to be quite as easy because we don't have x. We don't just have x, we have 2x plus 3. But it's no different from the zero product property. We need this quantity to be 0 or this quantity to be 0 in order to make y 0 for the x-intercept. Okay, so we need to say, all right, when does 2x plus 3 equal 0? Or when does 4x minus 1 equal 0? So we'd subtract 3. We would add 1 here. We would divide by 2. And over here we'd divide by 4. Okay, so we have the x-intercepts, negative 3 halves and 1/4. Now the vertex is going to occur halfway in between those. So we need the average of those two. So it would be negative 3 halves plus 1/4 divided by 2. We need to add these up here. So we'd get negative 6 fourths plus 1/4 divided by 2. So this would be negative 5 fourths. Negative 5 fourths divided by 2, so times 1/2, which would be negative 5 eighths. We know the x value of the vertex. So the x value of the vertex is going to be negative 5 eighths. We also need the y value. So if we know the we know the x value, so we need to figure out the y value. So we need to plug that into the original equation. So it's going to be y equals the quantity 2 times x, so 2 times negative 5 eighths, plus 3. So I plugged it into the first quantity. Then I'm going to go 4 times x, so 4 times negative 5 eighths, minus 1. Okay, so we need a little simplifying here. 2 and 8 reduced to 1/4, so this would be negative 5 fourths, plus 3, which is 12 fourths. Okay, 4 and 8 reduced to 1/2, so negative 5 halves, minus 2 halves. So this gives us 7 fourths times negative 7 halves, which would be negative 49 eighths. Negative 49 eighths. All right, not that easy, but that's because the x-intercepts were not real easy to come up with to start with, but that's how you'd come up with the vertex without a calculator especially. So your Chapter 12 test, be looking forward to that, is going to be without a calculator, so you'll need to know these methods to do without a calculator. All right, how does changing the a value affect the graph of y equals the quantity x plus 4 times the quantity x minus 2? So right now the a value is 1, but how does changing that affect the graph? I'm going to open up GeoGebra and we'll play around with some sliders, and hopefully you can pick up the idea of what we're trying to show you here. Okay, in GeoGebra, I've created sliders for the x-intercepts and for the a value. But we're just looking at the a value for right now. The a is 1, as you saw in that first one. Okay, so if I change it to 2 or so for something, what happened? Well, got a little further down here. The minimum became further into the negatives. Okay, so if I make that like 3 or 4, as I increase this, notice what happens. Okay, it just increases faster and faster, but the minimum gets lower and lower. Now, what happens if I change this to a negative? You should realize if I change it to a negative, it just makes the graph open down, and now we have a maximum point, and it would just get higher and higher. Okay, but notice what didn't change was the x-intercepts. So watch as I move this, the x-intercepts don't change. They stay at -4 and +2. Now let's say I want to change the x-intercepts. I would just move my slider here. Okay, so let's say I have x minus 6, and now I have x-intercept at 6, and let's move this, let's say to 1. Okay, so I'd have x minus 6, x minus 1, so I have x-intercepts at 1 and 6. The a value is just going to affect where the vertex is, but not where the x-intercepts are. Okay, so showing you the pictures again here. So if the a value is 1, we had a vertex at -1, -9, but the x-intercepts didn't change. Okay, so if we change this to 2, the vertex, where the vertex occurred does not change, just the y value changes, and the x-intercepts didn't change. As it changes to a -1, now it makes the vertex a maximum, and it opens down, but the x-intercepts don't change. And if it changes to a -3, the vertex x value stays the same, y value goes to 27, so it gets kind of a little bit steeper. Okay, if you show them all on one graph, you can see all the x-intercepts are the same, but where the y value of the vertex occurs, or whether it's a minimum or maximum, does change. So that's how the a value changes these graphs. All right, that wraps this up. Your assignment will be 12-3, page 733, number 2 through 20 evens. Thanks for watching, and we will see you next time.